My today's session will be based upon a special type of group which is called permutation group. As you know, a group is a kind of algebraic structure where two things are involved. One is the set, a non-empty set, and another is an operation, a binary operation. And the algebraic structure consisting of these two items is called group if it satisfies few properties, like number one is associativity. I'm not writing in details. Existence of identity. Number three is existence of inverse. And in some books, they talk about the closure property also. Closure property of the structure, which goes like this, that for any xy belonging to G, x star y also belongs to G. This property is called closure property. But I have not mentioned closure property here. I have not put the closure property. I didn't number the closure property as one of the points, because whenever I say that star is a binary operation, if I say like this, then by the definition of binary operation, it is already clear that the closure property is being satisfied, because that goes with the definition of binary operation. If I say that star is any operation, then I have to mention the closure property explicitly. But as I'm writing it as binary operation, then I don't have to mention it separately. So closure property is there hidden in the binary operation itself. So if this is the condition, then the structure is called group. Not every group is a commutative group, but if for some group one extra property is satisfied, like say for example, x star y is equal to y star x for all x belonging to, for all xy belonging to G, if this is satisfied for a particular group, then one extra property, let us number it by 4. Then if this 1 to 4 up to the properties 1 to up to 4 are satisfied, then such type of group is called commutative group. Or abelian group. All these things were discussed earlier in one of my classes. I am just recapitulating the thing once again. Now, often we actually try to find out group which are commutative or abelian. If these types of groups are obtained, we become very happy about it. But it is not always the case, because there are some other groups which are also very important, but they are not commutative group. So one such group which is commutative, which is not commutative, is called a permutation group. So permutation group, which I'm going to start today, is you are going to see that this group is a kind of non-commutative group. So permutation group is an example of non-commutative group. So I could have told this later on, but I think this is a very important point which you must note down. Okay, so I'm saying it in the beginning that it is a kind of non-commutative proof. Not only that, in algebraic structure, two important things are there, as you know. One is the set, which is non-empty, and another is the binary operation star. Now, if we consider the set capital G to be non-empty, if G is non-empty, that means the cardinality of G, cardinality of the set is actually the number of elements present in the set. The cardinality of G is not equal to 0, or you can say G is not equal to 5. So for example, two things may happen in this particular case. One is the cardinality of G is infinite. G contains infinitely many elements, or G can be finite. Okay, these two things can happen with respect to the cardinality of the non-empty set capital G. Permutation group is a kind of group which is a finite group. That is also a very important point that I want you to note down in your copy. So today I'm going to start a group which is called permutation group, and it is a special type of finite non-commutative or non-abelian group. It's a very important point. And what is the meaning of this word permutation? Is it something new? The answer is no. Permutation, we already know that if there are n different items, then these items can be arranged among themselves in n factorial ways. Okay, and especially if I consider three elements x1, x2, x3, then according to this rule of arrangement or the theory of combinatorics, we see that these elements x1, x2, x3 can be arranged among themselves in a 3 factorial, that is 6 ways. Okay, so this is called permutation. Permutation is what? The number of arrangements, the way by which a set of elements can be arranged among themselves. They change their position. Okay, so that is called arrangement. It is not about selection. But here, the perspective by through which we look at the permutation will be changed a little bit. We will look at the meaning of permutation will remain same, but we shall look at it from the perspective of the function. So now we are going to write the permutation with respect to a function. Okay, so how can we do so? That we are going to learn in our today's class. Now you see that if I ask you to write all the possible ways by which these elements x1, x2, x3 can be arranged among themselves, I know what you are going to do. You are going to write them as follows. Okay, you will write it as x1, x2, x3. That is the one way. And then you are going to write x1, x3, x2. Then you are going to write x1, x2, x3, x1. Then it will be x3, x2, x1. Two more. x1 x1 x2 x3 x1 x3 x2, another will be x2 x1 x3, and then we'll have another one will be there. One, two, three, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 2, 1, 3, 1, 2, x3, x1, x2. These are the 6 possible ways by which these elements can be arranged among themselves. So you will write it in this particular manner. But since I have already told you that the perspective by which we will look at the arrangement will be different in today's class. So if you ask me that how am I going to represent this permutation from the perspective of the a function, that I'm going to write in the next page. That in today's class we are going to represent them as follows. So I'm going to show you that. First of all, what am I supposed to do is that we already know that there will be 6 different arrangements like that. So I will write, first of all, I will write all the left hand sides as this. Okay, so let me fill it up first of all. Okay, now I'm going to fill up the right hand side. So one way is this, another way is another way, and we have then we have, and after that we have. So see, what have I done over here? I have written the left hand side. The left hand side of this is are same for all the 6 cases, but the right hand side are changing. Let me just check whether I have written all the different distinct items or not. 1, 2, 3, 2, 1, 3, 3, 1, 2. Oh, that will be 1. Sorry, this will be 1, 3, 2, 2, 3, 1, 3, 2, 1. All these items have been written, distinct items. What is happening over here? You see that left hand side remains same, but the right hand side is changing. Now I'm going to introduce a function. I'm going to introduce a function sigma over there, sigma. So we can say that under this x1 is the image of this element x1 under the function sigma. So we can write sigma over here in this manner. Okay. I'm putting sigma like this on the arrowheads. I can say that this change is being made with respect to the function that I have defined, which is called sigma. Or you can say that this x1 is the image of x1 under sigma. This is the image of x1 under sigma. This is the image of x2 under sigma. This is the image of x3 under sigma. This is the image of x1 under sigma. This is the image of x2 under sigma. This is the image of x3 under sigma, and so on. You just fill it up, and so on. So we can look at all these elements on the right hand side as an image of sigma. Okay. Now we have introduced a function over here. Now this function, because we know that to every function, there is always associated a domain and a range. To every function, there is always associated a domain. First of all, when we talk about a function, we have to be very clear about the domain of the function. As for example, if someone writes fx equal to x square, this doesn't bear a meaning. This doesn't bear any meaning, because I do not know, first of all, as you have already known from the mathematical logic, that this context is not clear over here. We do not know whether x is rational number, real number, or natural number. But if someone writes that fx equal to x square where x belongs to R, that means we know that we are choosing these elements from the set of real numbers. Okay, so when we are introducing a function and we are looking at the right hand side as an image of the elements of the left hand side under the function sigma, that means first question that comes over here in this particular case is that what is the domain? What is the domain of sigma? Okay, now you see that in this particular function, in this particular representation which I've written above, the left hand side is actually fixed. If I name the left hand side elements, if I contain the elements written on the left hand side, that is x1, x2, x3, by the set A, in the set A, then I can say that domain of sigma is actually, the domain of sigma is actually the set capital A, which is x1, x2, x3. Okay, and second question that comes to our mind is that what is the range of this function sigma? What is the range or codomain, whatever you call it, of sigma? Okay, so if you carefully look at it, you will find that range of sigma or codomain of sigma here is also x1, x2, x3, but their positions are being changed. Sometimes x2 is x2 can sit over here, x1 can sit over there. Sometimes you can interchange the position of x3 and x2, but also you know that in the set we are not bothered about the position. We call it the set's definition is as the set is defined as a well-defined collection of distinct objects. So whenever we talk about set, if I consider that this is a set, then this set and this set, they are actually same. This is not the case with sequence. If I write 1, 2, and if I call it as a sequence, then 1, 2, and 2, 1, they are actually different. So since we are actually domain and range, they are both sets. So actually, whatever their positions are on the right hand side, they are containing the same elements, that is x1, x2, x3. So we have introduced the function sigma over here. That function has domain which is defined to be the set capital A, and range which is also the set capital A. So from this particular example, we can define our function, we can define permutation in the following way. So permutation, we are viewing permutation as a kind of function. So what is the definition? So we can build up the definition from here, from the above example. We'll first write, let capital A be a non-empty set. We always consider the non-empty set because it is the non-trivial case. If we consider empty set, that doesn't bear any meaning. So let capital A be a non-empty set. We shouldn't say that A contains 3 elements, because A may contain any number of elements. The above which was written is just an example. So let capital A be a non-empty set. A permutation from now onwards from now onwards will be defined as this. A permutation of A is a bijection, or rather I must say is a bijective mapping of A onto itself. That is called the permutation. This is the definition of permutation. We shall be using this definition from today onwards. And what is bijection? Bijective mapping means a mapping which is both one-to-one and onto. A mapping which is both one-to-one and onto. That is called bijective mapping. Okay, so we have defined the permutation in the following above manner. I hope that you have understood the definition of permutation. Now let us define what is permutation group, because here we are not here to study about the set, we are here to study about the group. So here goes your second definition of permutation group as follows. So let me write the definition first of all. Once the permutation is defined, how can we give an algebraic structure to it? Okay, a group G star, and we know that group doesn't come in the group, the set doesn't come alone. In the group, the set always comes with an operation, whatever operation it can be. Okay, so that's why it is called an algebraic structure. It's not called a set. So a group G star is called a permutation group. Is called a permutation group on a non-empty set capital A, non-empty set capital A, if the elements of G are permutations of capital A, and the operation star is the composition of two mappings. So in when we talk about the algebraic structure G star, which this called be a group, it's called a permutation group, where now it will contain all the permutations which will be defined on the set capital A, on the non-empty set capital A, and the operation star over here will be the composition of two mappings. Okay, so to get a permutation group, first of all, you have to define the set capital A. You have to be sure enough about the set capital A. If the set capital A is defined properly, then we can apply the permutation function on the set A, and the permutations which will come out of it, those will be included in the set capital G. Okay, the G will contain, so here actually you see there are two sets. One is this one and another is this one. So you have to be very careful about the meaning of these two sets. Capital A is this one. Capital A is this one, first of all. Let me be very clear. If I consider the above example, how can I write my permutations? How can I define my permutation group? Say, for example, in the definition of permutation group, first of all, you have to set the example of the set capital A on which the permutation will be defined. So if A is there, define the permutation sigma from A to A. Okay. And the permutations which we obtain over here, what are the permutations we have obtained? We have obtained the permutations like, let me write it in this manner for the time being, but it is not the usual way by which we write it. I'll show you the usual way after some time. So we are considering all these permutations inside and this particular set will be defined by capital G, where the operation which will be considering will be the operation will be denoted by star, which is the composition of the mappings. So you have to be very careful about the difference between the set capital G and the set capital A. What is the composition of mapping? You know that if we consider a function f from A to B and another function G from B to C, then the composition of F and G will be denoted by F dot G and is defined as F dot G X, which will be equal to F of G of X. That is the definition of composition of two mappings. Okay. And the composition F dot G will be from the set capital A to set capital C. Now, here different sets are not there. Here only one set is involved, that is capital A. Sigma is defined on it. So how we are going to define this composition in this particular case with respect to the set capital G? How we are going to do this? Because the composition operation will not be applied on the set capital A. The composition operation will be applied on the set capital G. So if I denote this composition by star, we are not saying that A star is a group. We are saying that G star is a group. So we'll play with the elements of G star. We'll not play with the elements of A. The elements of A have helped us to form the elements of capital G only. Okay. But let us now, before I go deep into the discussion of composition of this composition mapping, which will be applied on the set capital G, first of all, I have to talk about the notation which I'm going to apply over here. The elements of G in this permutation theory of permutation group will not be defined in the following manner. It is not the usual notion by which we actually represent the elements of capital G. So what is the notation? What is the notation by which we can redesign it? So notation to represent the elements of G will be as follows. What we are going to do is that, first of all, we are going to write x1, x2, x3, kind of matrix we form, and then we are going to write its image under the operation sigma. So first element is x1, x2, x3. That means here in this element, the image of x1 is x1, the image of x2 is x2, the image of x3 is x3, and so on. In this manner, we are going to write all of these elements, all of the 6 elements. So let me write it. This is how we actually represent the elements of the capital G, where the row 1 represents the pre-image and row 2 represents the image. Okay, so from now onwards, we are going to represent the elements of capital G as follows. This is the representation, this is the notation. So in general, what I have done, actually I have written in general, if you want to express these elements, actually I have written in the following manner. So we have written x1, x2, x3, and if sigma is my function, then actually I have represented in the following manner. x1, x2, x3, and below we have written sigma x1, sigma x2, sigma x3, which are actually changing from element to element represented in capital G. Okay, so that is how, this is the notation by which we are going to represent the function. Next, we are going to discuss about, in the light of this, we are going to discuss about a very special group which is called, okay, I'm going to name the group later on, but let us see what I'm talking, let us try to find out what I'm talking about. In the previous pages, we talked about the general set capital A. A general set capital A which contained three elements x1, x2, x3. If we take capital A to be a set which is denoted by I3 and it contains 3 numbers, first three natural numbers 1, 2, 3, then we know that the set of all permutations which can be defined on the set I3 will form a group under the operation as defined in the previous page, star, which is composition of 2 mappings. Okay, and that group capital G right now will be denoted by S3, because in the previous page we just selected a general arbitrary set capital A. So a general notation capital G were used to represent a group. But right now I have changed it to a special case, which is I3 containing 3 numbers, first 3 natural numbers. So obviously, the notation to represent the permutations defined on I3 will be changed, and now the group capital G is specifically denoted by S3. We can instantly say that S3 will contain how many elements in it? 3 factorial, that is 6 element. Such a element, such a set S3 is called symmetric group. Symmetric group. We are going to discuss on symmetric group in the next session of today's class.